2, 1. All right, so in this video, I'll talk about trying to figure out all the possible combinations that you would have from a set of distinct items, or maybe not a set of distinct items. So when you're doing combinations, we know, okay, that we can have, n number of items, and then we can choose any number of them, and then we can find out exactly how many combinations exist. Now, if you are, so in this, for simplicity's sake, let's say you're given two distinct items and they're coins, a 10-cent coin and a 5-cent coin, and you wanted to find out all the possible combinations or all the possible sums that you can create out of these, then what you would actually be doing is you would be saying the following. So you'd say, okay, so I have two coins. Now, of course, I can go ahead and say, well, I don't want to choose any of them. So I would have to choose 0. So there's only one way to get an empty set to do that. And then I can go ahead and say, okay, well, I have two coins. I can also choose just one of them. And there's two possibilities. You either choose the 10-cent coin or the 5-cent coin. And then, lastly, you would have had to choose 2, which means you have chosen all the coins. And if you would do this, you would get the total number of combinations to be equal to 4, right? So we are going from just choosing a particular number from a distinct number of items to all the possibilities that we could possibly get. Now, if we had 3 coins, so we would have to go about, and we would say, let's say if there was a 25-cent coin as well, then we would have said, okay, well, I guess there's 3, choose 0. There is 3, choose 1. There is 3, choose 2. And then there is 3, choose 3. Okay, and then we would get a certain number of them. Now, this pattern of the summation that you would have, so meaning that we would want to find out all the possible combinations. If you actually recall Pascal's triangle, right? And when we talked about Pascal's triangle, you noticed that the sum of each row actually had one particular nice thing about it. What it had was, so in this case, because we were choosing 2 coins, right? You noticed that the answer was 4. And here, okay, so if we had 3 coins, so 3 distinct coins, then we would kind of be in the third row of that Pascal's triangle. And you may recall, okay, that the total number of possibilities, or when you're summing up the entire row of a Pascal's triangle, which is nothing else but just doing all the combinations, was equal to 2 to the n, where the n actually stood for the row that you're referring to. So with the 2 coins, 2 to the power of 2 is equal to 4. And if we're going to take 3 coins, we would have had 3 to the power of 3, which would actually have been equal to 8. And you can go about and you can see that that is indeed the case that you would have. So you would have 1, plus, this is 3, plus 3, plus 1, which would have given you 8. But we don't want to be doing the summation all the time. It is much easier to use this, right? In terms of our actual formula for the total number of possible combinations with distinct items. So in short, most of the time, we don't really count the empty set, right? So if you wanted to find out the total number of combinations, then really it would have been 2 to the n minus the one empty set, unless you want to include the empty set. But that would have been your formula. And from Pascal's triangle, that's exactly what we talked about. And maybe I'll put up a link up above there to that Pascal's triangle and then the discussion on that summation. It was one of the nice properties of the Pascal's triangle. Now, what would have happened if we didn't have distinct numbers? What if we had instead, okay, instead of having just, let's say, maybe one 10-cent coin, maybe we had two 10-cent coins. So if I would take this, okay, I'm going to take this and then copy it. Okay, and I'm going to paste it back in here. Okay, and then, you know, say that, oh, okay, well, what if I had, you know, 2 of these? So now they're not distinct, so how would I count my total number of possibilities that I have in here? Now, what I haven't mentioned to you above, that in order to actually find this and where this particular formula, okay, comes from, so 2 to the n, is from this interesting fact. So maybe what I'll do is maybe I'll kind of shift this down a little bit and just mention to you that you can look at this at a much different way. So what you can say is, okay, I have 2 distinct items that I can choose from. Okay, and for instance, for the 10 cents that I had, the way that you could have thought about this is you could have said that, okay, well, I can include it in counting the 10 cents, or I don't include it, which means I really have 2 possibilities here, which means I include it or I do not include it. Okay, so that is 2 possibilities that I can have for that 10 cents. And then for the 5 cents, I can do exactly the same thing. I can say, okay, well, I can include my 5 cents, or I will not include that 5 cents. So those are 2 possibilities that I would have. So this would have been a 2. And notice, okay, so this is just a multiplicative property, right? Where I have 2 ways of picking something, either picking it or not picking it. And then the second item, again, I can either pick it or not pick it. So that would have been 2 times 2, which again would have given me 4. And that's actually where the formula comes from. So that's 2 to the n. Because each time I have 2 choices to pick from, either include something or not include something. And if you had 3 items, it would have been exactly the same thing. So if those items were distinct, what you would have had was, let's say if there was another, maybe a quarter or something, then you could have said, okay, I'm going to either include the quarter or not include the quarter. And then the multiplicative property comes into play. So it would have been 2 times 2 times 2. Or if you have n items, it's going to be 2 to the n. And then again, don't forget, you know, that sometimes, okay, depending on your application, you may want to subtract the empty set when nothing is included. Because that is a possibility, right? The 10 cents is not included, the 5 cents is not included, and then let's say the 25 cents was not included, and then there's nothing there, right? So just keep that in mind. So extending this to something of this particular nature, right? So what would I have? If I wanted to count all the possibilities, except now I have 2 coins that are 10 cents, and then here I still have only 1 coin. So here I can either include 1 10 cent, I can include 2 of them, or I can include none of them. Which means instead of having 2 possibilities, now I have actually 3 possibilities. Don't include it, include only 1 of them, or include 2 of them. So if in here I would have said, okay, so this is actually 3 possibilities that I can have. Not including only 1, and including 2 of them, right? And then for here, well, I only have 1 coin, so I can either include it or not include it. So this still sticks it with 2. So that means that this is actually going to be 6 total possibilities that I can have, and I can list them all if I wanted to. But it's much easier to think of it this way. So you can probably now guess and extrapolate this, that if one item is actually repeating, and then you're going to be either including them or not, you just simply count, okay, how many of those items do I have, right? So let's say within here, what I had was, this was only 2, okay, but it could have been 3, it could have been 4, it could have been 5. So you always pick the total number plus 1, because the plus 1 just means that you haven't included any of them. So I would call this, let's say, n, 1 plus 1, all right? So that is how many of the first item that you have, which is n, 1 of them, plus the empty set. So those are all the possibilities. And then you're going to be multiplying it, okay, by how many of the items that you have, so in your second spot, plus 1, and then multiply, and then you're going to keep multiplying it until, you know, you have certain number. So I don't know how many, okay, of the items that you have that you would be able to do this. So let's say n, okay, and then this is to the m plus 1, all right? And then you just do the multiplication. So when you start multiplying them through, then that's something that will give you the total number of possibilities. So for instance, you know, if I remove this, I'm going to just do this and give you an example. So let's delete that. Let's say I had not necessarily coins, but maybe, you know, I had 5 Red Bulls, okay? I had maybe 3 yellow, okay, Red Bulls. And then maybe I had, I don't know, maybe 9, okay, blue Red Bulls. And then I wanted to find out, okay, how many total number of combinations would I be able to pick from all of these? Then you would have said, okay, well, my N1 here is 5, so I can pick either no Red Bulls, I can pick 1, I can pick 2, I can pick 3, 4, and 5. So those are 6 choices. So this would have been 6 multiplied by, so from the yellow, okay, this would have been 4, so no yellow balls, and then either 1 or 2 or 3 or 4, okay, and then so on, okay, and then this one would have been 10. And now when you multiply this entire thing, so 6 times 4 is 24, times 10 would have been 240, total different ways that I can choose, right? And now you can, if you want to remove the empty set, so this formula that you have would have been all of this, and then, you know, don't forget that you can subtract -1 at the end if you want to remove the empty set, meaning you haven't picked anything. So if you only have items that are completely distinct and you have only one of them, then this formula will do, because it makes sense. You either pick it or not. If you have more than one of those items, then you kind of have to extrapolate this to this formula. All right. Now, here is one, you know, other example that you can think about. Okay, and then I'll end this particular video. So let's imagine that we have maybe a swimmer. All right, so we have a swimmer. And then that swimmer's coach, okay, is going to be entering this swimmer into a competition. And the competition has, let's say, maybe 4 different style of races. Maybe it has a 50-meter freestyle swim. All right, maybe it has that. Okay, it may have also maybe a 100-meter, I don't know, fly. So you may know something about swimming or not. So butterfly. It may have, you know, let's say maybe a 200-meter backstroke. All right. And then maybe lastly it has maybe another 50-meter. Okay, and then maybe this is breaststroke. All right. So those are all the 4 different events. And then the coach is asking themselves, all right, so for this particular swimmer, what are all the possible combinations of events that this swimmer could swim? Okay, so it could swim nothing, right? It could swim only the 50-meter free, right? It could swim maybe the 50-meter free and the 100-meter fly, all right? Okay, and so on. So all the different combinations. So what would this be? Well, we have 4 items, right? So this is 4 items that we would have. Now, there's only 1, so these don't repeat. So that means I would have said, okay, well, this is 2 to the power of 4. And if I want to remove, okay, that the swimmer, you know, obviously will not swim anything, so I'll take the -1. And this would give me, so 2 to the 4, so that would have been 16 minus the 1. So there are 15 different possibilities that the swimmer could take on. So if you are ever asked to find out all the possibilities, you know, you can use these formulas and kind of thought process behind it. All right. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.